I'm Jessica.
And I'm Ralph, and we're here to review the topic of area and volume of rotation.
First thing that we must do is define the topic. There are two types of area problems to be covered: area between a function and the x-axis, and area between two functions. Let's begin with area between a function and the x-axis using the function f of x, bounded by two vertical lines as an example. We are trying to find the area between the function, beneath the function between the two vertical lines represented by the shaded region here. To do this, we must integrate the function f of x on the interval between the two bounds, with the one farthest left being our lower bound and the one farthest right being our upper bound. What we are doing by doing this is finding the approximation of the area of the shaded region. The bounds in this problem represent our starting point, which is the lower bound, and our ending point, which is the upper bound. The lower bound is always placed on the bottom of the integration symbol, and the upper bound is always placed on the top of the integration symbol. This is exactly like finding definite integrals. We can look at the second type of problem, which is area between two functions. Let's use the functions f of x and g of x, and find the area between them represented by the shaded region. The bounds in this type of problem are where the two functions intersect, so here and here. The bounds can be found by setting the two functions equal to each other and solving for x. Now that we have found the bounds, we can use them to find our area. In this type of problem, what you will be integrating is the higher function minus the lower function. In this case, f of x is higher, so it will go first, and g of x is lower, so it will be subtracted from f of x. The lower function is always subtracted from the higher function because you cannot have a negative area. Now that the integral is set up correctly, we can find the value of the shaded region. Now that we understand the topic, let's try a few practice problems. This problem is asking to find the area between f of x, which equals sine x, and the x-axis from 0 to pi. So first you're going to set up your integral with 0 being your lower bound and pi being your upper bound, sine x dx. So you're going to integrate sine x, which is negative cosine x, and then you always subtract your lower bound from your upper bound. So you're going to take negative cosine of pi minus negative cosine of 0. And negative cosine of pi is negative 1, and negative cosine of 0 is negative 1. So, and since you have a double negative, it's going to cancel out to be 1. Minus negative 1 is going to be 1. So 1 plus 1 is 2. So the area is 2. Second practice problem is asking you to find the area between f of x, which equals the square root of x, and g of x, which equals x squared. First, you're going to have to set f of x equal to g of x to find your bounds. After working out, you get your bounds to be x equals 0 and x equals 1. Going back to your integral, x equals 0 is going to be your lower bound, while x equals 1 is going to be your upper bound. And since f of x is higher than g of x is going to be subtracted from f of x. After working it out, you're going to plug your upper bound and then subtract your lower bound. And after working it out, you're going to get that your area equals 1/3. A variation on the area problem is when a problem asks you to find the value of a line that passes through the shaded region that would create two equal areas. You could do this with both types of area problems, and to do this you would set the integral equal to itself but adjust the bounds to fit the problem. So let's say that line K divides the area in two and that the bounds are from 0 to 4 for the area represented by the shaded region. You would set up the integral normally, but make the bounds go from 0 to K, and then set it equal to itself, but make these bounds go from K to 4, and then solve for K.
Now that we have explained area, it's time to define volume of rotation. There are two types of volume of rotation problems. One is rotating about the x-axis, and the other is rotating between two functions. Let's begin by rotating around the x-axis using the function f of x, bounded by the lower and upper bounds represented by the shaded region. To find the volume of this shaded region rotated around the x-axis, we must first visualize what we are doing. To see this, we can draw a rectangle from the x-axis to the function, and then draw a rotation of that rectangle. This is called disk method because what you have created by drawing this is a disk. Now that we understand disk method, we can use it to solve for the volume of rotation. We must take the integral of the function, like in the area problem, but we must square the function. Then we continue as usual by integrating and then solving for the definite integral using our lower and upper bounds. Now we must define volume of rotation between two functions. To find the bounds, we set the functions equal to each other and solve for x, like in the area problem. Let's use functions f of x and g of x, and the shaded region which will be rotated about the x-axis. To find the volume of this rotated region, we must first visualize it by drawing a rectangle from the lower function to the higher function, and then draw the rotation of that rectangle. This is called washer method because the shape that is created is a washer shape. Since f of x is higher in this problem, we must subtract g of x from f of x in the integral, just as we did in the area problem. But we must square both functions for it to be washer method. Then we can continue as usual by integrating the functions and then plugging in our bounds to solve for the definite integral.
First practice problem asks you to find the volume of rotation between the function sine x and the x-axis from 0 to pi. You would do this by plugging in your function and squaring it. Then you would take the integral of that and plug in your bounds to find your definite integral. Now let's move down to the second practice problem. It asks to find the volume of rotation between the function square root of x and the function x squared about the x-axis. You would do this by plugging f of x first because it's the higher of the two functions, and then plugging g of x second because it's the lower of the two functions. You would square both of them and then take the integral of this, plug in your bounds to get your definite integral. Few variations to the two types of volume problems, and each variation could be applied to both problems. The first variation is rotation below the x-axis, which is when the volume of rotation is below the x-axis as shown by the diagram here. Most students will be tricked when setting up this integral because they will think that f of x is the higher function, but really g of x is the higher function when rotating about the x-axis. The rule is that the higher function is always the one that is furthest from the line that is being rotated around. So you would put g of x first in the integral and then subtract f of x from that. Let's move down to the second variation. The next variation is that the volume between the two functions can be rotated around any horizontal line. Let's look at this diagram of f of x and g of x when the volume of rotation is being rotated about the horizontal line y equals 2. To set up this integral, you would set it up normally but subtract 2 from each function within the square. If it asked to rotate around y equals -1, then you would add 1 to both places. This variation could also be applied to rotation of volume between a function f of x and the x-axis. But you still do the same thing by subtracting or adding the value of the line to the function within the square. Variation is rotation of volume around the y-axis. To do this, you must first set all of your functions and bounds in terms of y. Most students will remember to change their functions but not their bounds, which are very important. Then, you would plug in your bounds and integrate normally after that. Let's move down to the second variation. Another variation is that the problem will ask you to rotate the shaded region around a vertical line, let's say x equals 4. You must again set all of your bounds and functions equal in terms of y, but then subtract 4 from each function within the square. If the vertical line was, let's say, x equals -4, then you would add 4 to both functions within the square. You may also be asked to find the value of a line k that passes through the shaded region that creates two equal volumes of rotation, just as you were in your variation on the area problem. You would again set the integral equal to itself and adjust the bounds to fit the problem. Here we have it bounded at x equals 4 and 0. So you would set your bounds equal from 0 to k, and then on this side from k to 4, and then integrate both sides and solve for k. And that covers all the variations on the two types of volume of rotation problems.